Alright, I'll be giving a quick solution to the question one of the assignment and of the exam question. So it said, given the intrinsic carrier concentration of the material is given by this, and this is Ni is equals to A T3 raised to power 3 over 2 Eg over 2 kBt. So this, we are meant to plot a graph of using the band gap of silicon and GaSa germanium. So this is the solution to that. Alright, so this is the solution. So we took each temperature, so at 200 degrees Celsius we calculated the intrinsic carrier concentration for each temperature. So at 200 degrees Celsius we got 2.742 using the formula that was given us there, and calculated at 400 degrees Celsius at 600 degrees Celsius. And we also calculated for silicon at 200, at 400 and at 600. So we plotted the graph. This is just a sketch of how the graph will look like. And the second question they said, okay, let me quickly go to the second question. So second question said that using the attached CMOS inverter data sheet, which this is the data sheet here, and they said that we should calculate the noise margin supply voltage of 5.5, and we should sketch the voltage transfer curve showing the switching point. So this is the from the data sheet. We already know that to calculate our noise margin high and our noise margin low, this is the formula. VOH is equals to NMH plus VIH. So we made NMH solve of formula. From the data sheet we got VOH as 3.94 and VIH as 2.0. Then we minus it together, we got 1.94. Then NM low is from the data sheet we got 2.8 minus 0.36, we got 2.24. So we sketch them here. So the third one was that they said we should derive the sizing ratio. So the sizing ratio, Kp is equals to the width divided by the length of the PMOS multiplied by the mobility of the PMOS times the capacitance. Then for that of the NMOS, the width divided by the length of the NMOS times the mobility of the NMOS times the capacitance. So when we take the ratio and we assume that the sizing ratio is unity, we get a relationship between the mobility of the NMOS and the division between the width and the length of that. So the third one, they said that we should draw the third question. They said we should sketch the input output pulse passing through the inverter showing the propagation delay. So to sketch this, because of the time, so we took all this data from the data sheet. We did the calculation and we calculated time propagation delay moving from low to high. This is it from high to low. This is it. And we got 6.9 nanoseconds, 7.9 nanoseconds from the data sheet. And this is the rising time and this is the fall time. So the last question, they said we should give a load of capacitance of 50 picofarad from maximum propagation delay, assuming 1 microprocessor determined. So since it is 1 microprocessor, it means that we are the COX that we are to use. The COX that we are to use is 1.75 femto. So we write out the calculations, and we did the C out is equals to this load capacitor plus this capacitance. When we added them together, we did the calculation, and there was a relationship between the input capacitance and the output capacitance, which is 3 over 2. Input capacitance is equals to 3 over 2 output capacitance. Then we did the calculation.